This video is sponsored by PCBWay.com. Hello guys and welcome back to the channel. Today I'm so excited because I just received the new version of the ARINC 429 PCB from PCBWay.com, the sponsor of this video. I know I already showed you a previous version of this PCB, but I made some improvements on the receiving part, which I'm going to test in the upcoming videos. Today we are gonna see the transmission part. So this video is dedicated to the ARINC 429 transmission. We're gonna see how the transmission works into the details. We're gonna see the hardware that I used and also the software that I used. The parts that I received from PCBWay.com are the PCB themselves, and I also designed some enclosure. So all the parts are flawless, and as you can see they are very nice and smooth, finished and reprinted. Actually this is I think resin printing or something. I really have to thank PCBWay.com for producing this PCB for me, and also printing this nice enclosure that you can see here. Ordering from PCBWay.com was quite easy. You just go on their website, you could clone quote. Now in my case I already had Gerber files exported from Fusion 360, so I went to the quick order procedure. I selected the Gerber file, which is usually a zip file. The system recognizes the parameters of your PCB. You have several options like the color. In my case I choose the nice blue color, and I also choose the STM soldering service. Once you have done that, you will submit the order for reviewing and quotation. For the 3D printed part, it's the same procedure. It's actually a bit faster because you just need to upload the STL file of your project, exported in my case always with Fusion 360. So I went ahead and soldered all the sockets for the ESP32, for the Ethernet module, and also for the in-out part. So we're gonna do like this. So we put the ESP32 here, the Ethernet module here, and then I'm gonna put the power supply here on plus and minus 5 volt. For this I'm going to use my bench power supply, and then I'm going to also use some oscilloscope probes on this channel here, the transmission one, to see what is the waveform. But before doing that, let's switch to the iPad and computer and understand how the transmission ARINC 429 works. So the main idea for ARINC transmitter comes from this web page. There is this guy, Stephen Woodward, who posted this nice circuit here. It's very nice because it doesn't use any expensive component. It actually uses components that can be retrieved quite easily, and they are not so expensive. And moreover, by studying this circuit, I realized that from what I needed to do, only this 4052 was actually needed for the purpose. All the rest is something that does FIFO memory things, but we don't need this with the ESP32. So the ARINC driver, it is just this 4052 IC connected in this way. We're gonna see it's very easy to implement. And then there is some filtering part. So here we can see the details how 4052 works. It's actually a 2-bit analog switch, and by selecting A and B 0, 1, we can connect one of these lines, two of these lines, to the lines here in the output. So in our case, we're going to use the A and B line, which will be selected by the ESP32, and the output of the ARINC will be on the X and Y lines. This is the schematic of the transmitter, which is implemented in the PCB. We have the ESP32, which will be interfaced via USB, Ethernet, or Wi-Fi. This is not very important. We can just change the firmware to have different interfaces. But what is important is that we have two lines. In my case, GPIO 13 and 14, which are configured as RMT channels, and the RMT channel is a very powerful driver from the ESP32, and gives us a lot of freedom for signal generation. We're going to see these more in details later when we're going to check on the firmware. So these two lines are connected to the A and B, and you see here how the other lines are connected. So we have X0, X1, Y0, Y1 connected to the ground together to the inhibit with the inhibit pin. Also the X3 and Y2 are connected to the plus 5 volts, and Y3 and X2 connected to the minus 5 volts. Thanks to this clever arrangement, we will be able to generate high and low speed ARINC signals. The rest is not very important. Actually, I used an op-amp to give a bit more power to the signal. I am using here a TLV9154, which is rail-to-rail op-amp, and it's quite fast. It actually gives us where is it, 20 volts per microsecond slew rate, which is enough for having also the high-speed ARINC 429, and the rest is actually filtering. There are diodes to smooth the transient, some filtering capacitors, and I also added these two resistors to match the impedance of the ARINC line A and line B. So here we are with the main firmware files for the ESP32S3. I remind you that all the files can be that we are going to use today can be found in my GitHub repository. And the main files are this Ethernet, of course responsible for the Ethernet connection, the ARINC, and this ARINC TX16.c, which is the main file. It's worth going to see what happens in the ARINC.c file, because the others are not very important. And inside this file, which is quite long, what is worth noting, actually this file can be much smaller, because the most important parts of these files are this routine here, which is the routine used by the RMT to create the clock signal for the ARINC generation. So we have this vector here. It's which I called clock items. It's a 32-bit item, and it's filled by zeros and ones. And we have also a duration specific, which we specify with this half period microseconds, which can be the half of the period of an high or low speed of the ARINC. Basically, this vector is filled always with the same kind of data, zeros and ones. Then after we have this, we need the second part, which is the ARINC data itself, which is going to be sent here. Actually, in this routine, we receive the 19 bits of the ARINC data. We reverse it, then we create a new variable called W31, where we put the label, the STI, the data, and the SSM. We compute then the parity, and then we send everything to this MOSI item, which is actually the second part of the RMT signal. So this is going to create a 0 or 1 pulse according to what is stored in the W32 packet. With the same half period we have defined, of course, for the clock signal. So the CD4052 uses a kind of SPI bus data. So we have the clock and the data, the MOSI itself. The rest of this routine is going to send the clock and the data to the RMT channels you see here. And basically that's it. All the rest is some files which are used to select between the low and the high speed to receive the data, the ARINC data over the UDP, over the Ethernet, and do the scan, or do all such kind of things that we can do in the GUI. So I connected the power supply here. I also connected the two oscilloscope probes to the output of the ARINC, and now let's go again to the computer and see what are the waveforms. So here we are on the computer. Once again, I have the remote oscilloscope screen here. I have trace number 1 and trace number 2 connected to the ARINC transmission line A and B. I also have here my terminal, and I'm gonna open with Python 3.12 a little GUI I set up to control the ARINC PCB. So here it is. It's quite simple. It uses the ESP32 Ethernet connection over UDP, and we can send 16 different labels plus 1. I'm going to show you what is plus 1 in a moment. So I have the ESP32 IP, the UDP port, and also the signal can be high or low speed. For each label, for each ARINC packet, I can type a different label. I can choose the SDI, also the SSM, and also the period, repeating time in milliseconds. And as I have 16 different packets, I can also choose how much time I want between two different packets. Also, if we go down, we have other controls. This data 19-bit editor is the editor. We can edit bit by bit from 1 to 19. The data, the real data transmitted by the ARINC. In this case, I have the number 90, which is selected here, and 90 in decoded in the ARINC is it's the hex number 5A, and it corresponds to bit 2, 4, 5, and 7 on of the ARINC signal. If we go down, we also have the encoding for the BNR, BCD frequencies. This we're going to see them probably when we are going to test real ARINC gauges. We also have here a list of ARINC standard ARINC labels and the decoding also that we can apply in each channel. And at the very bottom we also have this persistent scan channel. This is very useful if you want to scan one ARINC unit and you don't know exactly how what are the labels that you should send. In this configuration, for instance, if we enable this channel, which is going to be the channel 17, this is why I put 16 plus 1, it's gonna do a scan from label 0 to label 377, sending random data 19 bits. This is very useful if you want to scan and you don't know exactly what the unit is expecting to see, and you can see if the unit reacts. So let's go ahead now and see what is the ARINC signal we have. I have here channel number 1, which is enabled, but the scheduler is not yet enabled. Label 320 is transmitted with SSM and STI equal to 0, and this 90 data is transmitted. So let's start the scheduler, and we see something. So we see the ARINC data high speed here. You see that compared to the hold driver, it's not very nice like the hold driver. In particular, we see that the A and B are not super symmetric, but if we zoom, we see that the signal is not that bad. But the important point is to check if it's really a high-speed signal. So let me go ahead and activate for one channel. So I switch off one channel and I start to measure. Manual. Here we go. Let's do this. We are in high-speed mode, so let's measure the beginning of the signal and the end of the signal, which is right almost exactly 10 nanosecond is 9.6. Sorry, no, it's exactly 10 nanoseconds, microseconds. Which is the high speed, and we can see actually that we have 98 kilohertz, almost 100. Then half beat should be more or less half of it. Okay. The same characteristics are for the other channel, this one, and we can also have a look at low speed one. So let's see what happens when we change from high speed to low speed. And by the way, the interface changes immediately when we change something. The interface, it responds immediately and changes the signal output. So this is the low speed. Let me be a bit more precise here. Yes, like this. We have almost exactly 80 microsecond and a frequency of 12.5. Sorry. Here it is. Sorry, 12.5 kilohertz. So it works. Of course, we don't have the nice rising and falling gauge we have with the hold signal, but I can assure you it's gonna work anyway. We're gonna see that later. So here I have the logic analyzer, which is ready to capture the packets coming from the ARINC board. And here I have set up 5 different labels, you can see here, and some random data transmitter with SSM equal to 0. Only the label 0 to 4 is with SSM equal to 3. Let's start the schedule, and you immediately see that we acquired some packets. So let's see a little bit what we have here. So we have label T through 0 with parity OK, STI equal to 0, SSM equal to 0. Yes. Then we have label 034, and this is correct, with other data. The data decoding it can be everything. I mean, this is of course decoded with the hex decoding. Then what do we have here? Then we have label 024, which is this one, which is correct. And this should have, okay, yes, SSM equal to 3, yes. And then if we go on, we have label 120. Yes, 120, and now we should see label 344, which is this one. Yes, 344. Let's see now what is the time frame. So you see that once again we have label 230. Let's see what is the time space between two words. It should be let's take for instance the 034 and 024, which are, should be this one. No, it's okay. So yeah, let's see for instance between these two, 034 and 024. Let's measure. Let's see if we did it right. Almost. Should do this from here to here. So we are at 9.68 milliseconds, which is correct because the offset is yes, 10 milliseconds. And the same happens for the other ones. I don't go through all the measurements, but this is just to show that the interface and the hardware are quite precise. I want also to check if the signal is reliable. I mean, if over time the signal is stable. I have so far one label sending, and I'm going to set up an pass and fail of the signal. So I'm gonna get here, create from screen. We're gonna do this, create. So everything which is inside this mask is passed. And here we can see the result, the fail, the pass, and the total amount of waveform that are captured. So for the mask, okay, so I create. So I would like to be a little bit like this, and for the Y, I will reduce a bit the Y, and I will recreate this one. So, and then I will start acquiring data, and we see the result here. So far we have 100, 200 waveforms and 0 failed. So let it run for some minutes, and we'll see the results at the end. We have 0 failed, over 4,000 waveforms, and this is the high speed. For testing the PCB on real unit, I thought it would be nice to use this Airbus DDRMI. We can send several labels, one for the compass, another one for the VOR, and then another one for the ADF, because this is the version with VOR and ADF, and also for the DME distances. In theory, actually the unit works with high speed and low speed. The high speed is for the compass, the low speed is for the rest. However, in my case, I'm just going to use one single ARINC channel for everything. So in theory, we should use one channel for the VOR1, one channel for the VOR2, and the same for the ADF1, ADF2, and also for the DME. But once again, I'm going to use one single ARINC channel, and I'm going to distribute the ARINC signal through these bars here, so for the A and B. So here we have, let's start with label 230. Okay, I'm gonna send some random data here. Let's see if it moves. Yes. You see, I'm in high speed mode, but I found that this unit can work also in low speed for this label 230. It's not super stable, but it can be used. Let's go with VOR. Let's send data, some random data. Let's do the ADF, label 162. We can also do random stuff here. And DME. So if you like the video, please like and subscribe, and if you have comments or questions, please leave a comment on the bottom of the video. The software firmware is everything is available on my GitHub. You have the link on the video description. See you next time, then bye bye.